Okay. So, in constraint optimization, after studying the basic theory and also studying one basic method of solving constraint optimization problems, that is by simply trying to satisfy the KKT conditions. I said that we will next move ourselves away from methods and for a while concentrate on problems, and in that we will take up two special classes of constraint optimization problems. One is linear programming problem and the other is quadratic programming problem, because in some sense these two segments are easier. So, linear programming we have already covered. Now, next is quadratic programming problem. In that most of the basic material is there in the applied mathematical methods slides, slide number 283 to 286. So, we will cover that and then come back to the main page, this page, for the appendices and appendices basically, that is some elaboration and examples. Okay. So, quadratic programming. You know what is quadratic programming? That is optimization problems in which the objective function is quadratic and the constraints are or linear. So, that is a quadratic programming problem. Now, this is actually a little loose definition by which optimization scholars sometimes mean what has been said in the definition, or sometimes implicitly mean that the quadratic function is convex. Now, in this case, if the quadratic function is convex also, then it becomes a convex programming problem. Okay. So, now a quadratic objective function and linear constraints define a QP problem. Now, why this is special? In the case of linear programming problems, we noticed that that is special because that is easier, in the sense that the KKT conditions of a linear programming problem were all linear. In quadratic programming problem, what happens is that the KKT conditions, the equations that the KKT conditions give, they are all linear. It is a different matter that some of them are bilinear, okay, because they are the complementarity conditions. Other than that, everything else is linear, the equations. Okay. Let us see how. So, equations from KKT conditions are linear, and Lagrange methods therefore become the obvious natural choice, because we think that linear equations, solving linear equations is an easy task, okay, which is true also to a good extent. So, now first we consider the situation with only equality constraints, because that is very simple. So, there you will have a quadratic function like this and a bunch of linear constraints like this, and then when you work out the first order necessary conditions or KKT conditions, you will find only equations, okay. And see, from here by differentiation you will get q x plus c. So, q x is here, c has come here as minus c, and then from the derivative of a x minus b into lambda, basically lambda transpose a x minus b. When you differentiate this part, then you will get a transpose lambda. Okay. So, this is the first block equation. Okay. So, q x plus a transpose lambda equal to minus c, and the second block is what? Second block is simply a x minus b equal to 0, right. So, a x plus 0 into lambda equal to b, a x equal to b or a x minus b equal to 0, whatever way. Now, you see that what are the unknowns here? The optimal point x star is the unknown and the corresponding Lagrange multipliers are the unknowns. Okay. So, together they are coming here and these are all known, this coefficient matrix is entirely known. Not only that, this coefficient matrix is symmetric, and if the objective function is convex, really convex, quadratic convex function, then this Q is positive definite, that is if it is strictly convex, and if A is full rank, which you will expect, because you expect that these are all independent, linearly independent constraints. So, then this entire matrix is positive definite, and that means your favorite simplest pet Cholesky decomposition method can be used to solve this. Oh, however, it cannot be used here, because this entire matrix will not be positive definite, it will be indefinite, because of these zeros a number of eigenvalues will be negative corresponding to the dual space. So, Cholesky decomposition cannot be used, even though it is looking nice. This part is convex, the whole matrix will not be convex. Okay. So, in any case, in any way it is a system of linear equations and symmetric. So, whatever methods you use that and solve it and get x star and lambda, and that will be the complete solution. Okay. So, the coefficient matrix is indefinite. So, that you have to keep in mind. So, Cholesky you cannot use. So, this is if the constraints are all linear, and that is very simple. You just solve a system of linear equations and you are done. Now, if the constraints are not all linear, then what do you do? There are as usual two strategies. One is active set strategy and the other is slack variable strategy. So, in the active set strategy, with equality constraints and inequality constraints also, we work like this. First, we start the iterative process from some feasible point. Some feasible point means all the equality constraints are satisfied, and the equality constraints are satisfied either at equality, inequality constraints are satisfied either at equality or at less than. Fine. So, those which are satisfied at equality, they are the active constraints, because the current point x 0 is at the boundary of that. Okay. So, put them in the active constraints, and for the time being those rows of the active constraints you assemble with A 1 and B 1, and then make a big matrix A and a big vector B, that is this. So, construct active set of constraints as this. In A, the entire A 1 will be sitting, and those rows of A 2 will be sitting which are satisfied at the equality. Similarly, in B, the entire B 1 and those elements of B 2 will be sitting. So, this is the set of constraints which is for the time being for this iteration taken as equality constraints. The others which are inactive, but satisfied, okay, so they are for the time being left, and then solve this as a QP problem with only equality constraints, okay, from the current point to wherever you go, by the method that we discussed earlier. When you do that, how do we do that to begin with? So, from the current point we say, suppose we take a step of dk. So, x k plus dk. So, from the current x, that is x k, we take x k plus dk. So, that means we take a step of dk and then put this thing in the function half x k plus dk transpose q x k plus dk plus C transpose x k plus dk, and then simplify this and see what do you get. From here you will get one term which is half x k transpose q x k, that is a constant, do not worry about that, that will stay somewhere here, actually that is part of f of x k, right. So, the first element from this product and the first element from this product together is the current value of the function, that is a number, that is a constant, keep it here. Now, the second and third from here will be half dk transpose q x k and x k transpose q dk. These two are transposes of each other because q is symmetric, and so half plus half, it will become 1, and that is basically x k transpose q d k, which is the second element here. Okay. And the first element of here, this place, is this C transpose d k, okay, C transpose d k. And the fourth element from here, which is the only left element now, is half d k transpose q d k. Now, you have got the f x, that is f at the new point where you are planning to go, as this. As you see, this is a quadratic function in d k, and you try to solve this for the time being, because x k you already know. Now, you will say that, so what is the big deal? What is happening? We had a quadratic problem in x, now we have got a quadratic problem in d, but then the constraints for this quadratic problem will be simpler. What they will be? See, a times x k is b, and you are asking for x k plus d k, where also you want a times x k plus d k is also equal to b. That means, a times d k is 0. That means, the conditions on the quadratic problem now is this. This is the constraint, and you try to minimize this function subject to the constraints this. Okay. These are all equality constraints, fine. And you see, we have left this, because this is a constant. So, whether we keep it in the objective function or not, it does not matter. So, then we minimize this by that method. So, when we do that, we get the step, that means, we get d k and the lambda, fine. And now, you have to examine this d k step suggested by this solution and the Lagrange multipliers to decide to terminate, proceed for the next iteration, or revise the active set. How do we do that? Let us see here. The solutions you have got. Now, the Lagrange multipliers that you get from here, you classify them. Which of them are actually lambdas, and which of them are really not lambdas, but mu's. Those are the active inequality constraints from where they have come. So, note down all of these: d k full vector, all the lambdas corresponding to the original equality constraints, and all the mu's, which are the equality constraints here, but originally inequality constraints, and therefore, these are mu's and not lambdas. Now, what do you really examine? First thing, if in the solution d k turns out to be 0, that means what? The optimization step in this iteration is suggesting do not move. Okay. Then lambda k's could be positive, negative, 0, whatever, you do not know. So, whatever comes, you have to accept them. Mu's, you know that mu's should be all non-negative. So, this is what you examine. Are all the mu's non-negative? If yes, then you see you have satisfied all the KKT conditions, and that means this is a local minimum point. So, you stop. If not, then there will be some of the mu's which are negative, and whichever is the worst negative, that is the most negative, you say this particular constraint had no business sitting in the active set. Why? See this. This is the constraint. As it happens, you have taken the initial point here. Okay. This is your x k or x 0, whatever, say this is x k. Okay. And since you have taken the initial point here, or through some iteration you have landed here, so that is why this constraint was taken as active. Okay. And then since this was taken as active, so the algorithm is trying to stay on this boundary. Okay. And as a result, d k turns out to be 0, that means the suggestion is do not move from here, and the corresponding mu, that is the Lagrange multiplier corresponding to this particular constraint, turns out to be negative, and negative Lagrange multiplier corresponding to an inequality constraint means that if you go inward, then the function will decrease. Then why you did not go inward? Because this was given as the active constraint. Okay. So, this constraint has no business sitting in the active set. Okay. So, like that, none of the constraints for which the mu's are negative have any business sitting there, but in one step the party line is to drop only one constraint. So, you drop the worst one, and then since you have dropped a constraint, so from A and B the corresponding line you remove, okay, and then repeat this process, and then do this, see which case it falls in. Now, if in a particular iteration you find that the values of dk, lambda k, mu k give you this situation, dk is non-zero, that is a proper move is suggested, and if you move there x k plus dk, then that new point turns out to be feasible. Okay. So, that is one good thing. So, then you update it x k plus dk, x k plus 1, that is for the next iteration, and in any case examine the Lagrange multipliers and handle them in this manner. Okay. Then if dk turns out to be non-zero, that is a move is suggested, and the move is suggested to a point which is not feasible, that means some constraints are getting violated. That means you have to use a cutoff, exactly the way you did in linear programming problem. So, since you will use a cutoff, so you say full decay we will not take, that big step we will not take, we will take alpha fraction of it. Okay, propose this and determine suitable alpha. So, if in this particular iteration, in this particular step, you have retained all the active constraints as active, active means satisfied also, then how come the resulting point is becoming infeasible? The only way that can happen is that those constraints which were sitting inactive, some of them are on the way from x k to x k plus d k becoming active and then getting violated. So, up to becoming active we can agree we will not let them violate. Okay. So, that is why you have to consider each inactive constraint one by one. So, consider each row, ith row, that will give you a 2 x k plus alpha d k, this vector's ith entry less than equal to b 2's ith entry. Okay. So, ith row of that will give you this. Okay. Now, open this, alpha times ith entry of a 2 d k less than equal to b 2 I minus a 2 x k I. Okay. So, this thing should be less than equal to this thing, and make note that this is positive. Why? Because to begin with a 2 into x k was less than equal to b 2. Okay. So, this is positive or 0, non negative. Okay. So, then if this is negative, then you do not bother, that means it is getting violated behind, not ahead. If this is positive, then you take the ratio this by this, that means alpha equal to this by this. Now, you see each such inactive constraint, that is for each I you will get one such alpha, which will be the constraining step. Okay. The smallest one of these, smallest positive one you will take, only positive ones you will evaluate, okay, and the smallest one you will take, and that you take as alpha k, and then update x k plus 1 equal to x k plus alpha k d k, and that takes you to the next iteration. See this elaboration. Say you started from here and dk was this much, from this red star to this red star, this much decay was proposed, okay, as the optimization process in this particular iteration. Now, suppose there are 5 constraints inactive. Okay. So, first constraint boundary is this. So, that is cutting here. So, that means you cannot take this step, you have to take at most this much. The second constraint cuts like this, which gives you this. Okay. So, it is anyway larger than this. So, this fellow will rule, that because one fellow is telling that you cannot take larger than 0.6, another fellow is telling that you cannot take larger than 0.75. So, basically that means that you cannot take larger than 0.6. Yet another fellow cutting like this is telling that you cannot take more than 0.45. So, higher than 0.45 you cannot take. The next fellow, constraint number 4, is cutting like this, but that is behind. Okay. What it is telling, that ahead of this you can go whatever you want, fine. So, it is not putting any constraint, and this is the situation, the constraints which cut behind, that correspond to the negative elements here. So, that you do not have to bother. Similarly, this fifth one. Okay. So, fourth and fifth are not bothering you, because one cutting here, one is cutting here behind, another is cutting here behind. Okay. So, this is how you make the cutoff and take that as the next point and recalculate the active set there, because the fellow which defined the cutoff will now become active. Okay. So, this is how you operate active set theory, active set method. Okay. Now, how do you use slack variable method to solve this? This is a very funny method. What you do in the slack variable method for quadratic optimization, quadratic programming problem, is that you work out a problem which is a linear problem, linear complementary problem. Okay. So, complementary is the keyword here, and this is a slack variable strategy with inequality constraints. Make note, only inequality constraints, no equality constraints here. Okay. So, take this half x transpose q x plus c transpose x, the same thing, subject to this all inequality constraints and the typical element of a slack variable strategy. All the variables also you want to be non-negative. That means, so that they can impersonate as slack variables. But this we have already done in linear programming. So, we know that if the original variables of the problem are not like that, then you can forcibly make them like that by breaking each genuine variable into 2 fictitious variable. Okay. So, one x 3 can be broken into y 5 minus y 6, where both the y's will be non-negative. So, that kind of a trick you can always do. Okay. So, by all those trickery you have put the problem in this manner, and right now we are telling that all the constraints are inequality constraints. Okay, fine. Now, KKT conditions. So, if you find this from here to jumping to these KKT conditions immediately difficult, then I will show you the appendix here. First of all, make note that these are all positive. Why x is positive? Because that is the way it has been given, the problem has been given or formulated. Why y is positive? Because y is the slack variable here. Okay. Ax plus y equal to b. Okay. And mu is the set of Lagrange multipliers corresponding to this set of inequality constraints, and nu is the set of Lagrange multipliers corresponding to this set of constraints. Make note that these are also constraints. Okay. So, if you write this thing in this manner, then you can directly see the objective function is this. One set of constraints is g less than or equal to 0, a x minus b less than or equal to 0, and the other set of constraints is g bar, that is minus x less than or equal to 0, that is here. Okay. So, the Lagrangian will be this whole thing plus mu transpose this plus nu transpose this, and that is why minus nu transpose x. And when you try to find out the optimality conditions from here, then you basically differentiate. So, with respect to x. So, from here you get q x plus c plus a transpose mu minus nu, this equal to 0. This is one set of optimality conditions, optimality constraints. And this is anyway feasibility condition, a x minus b less than or equal to 0, or by the introduction of slack variable you can say a x plus y equal to b, where y is of course non-negative. So, this is one set of feasibility conditions. Another set of feasibility conditions is here, x and y non-negative, y because it is slack variable, x because that is given. Mu and nu are also non-negative. These are actually optimality conditions. In the KKT conditions you get this for ensuring optimality in the cone of the cone of the feasible directions. Okay. And these are the complementary conditions, x transpose nu because corresponding to these constraints you have nu as the Lagrange multipliers. So, each pair x j nu j should be 0, and similarly for this set you have mu j y j 0, each pair, product of each pair. Okay. So, these are the complementary conditions. So, these are all the KKT conditions that you have. Now, from here this slack variable strategy constructs a linear complementary problem in an extremely peculiar manner. Let us see how. From this equation, first get hold of all the equations. Okay. So, here is a set of equations and here is a set of equations, okay, which are linear. These complementary conditions we will leave for the time being. Okay. These are also equations, but these are bilinear, but this we will handle separately. We will not put them through the standard equation solving process. Okay. So, otherwise these are the two sets of equations. So, what we do, this q x and a transpose mu you keep on one side, q x plus a transpose mu plus c, that also for the time being we have kept on this same side. This nu we have thrown on the other side. Okay. And then here we will do a little funny thing. We will first of all take this one and then take a x on the other side, that means minus a x plus b. So, keep minus a x here and plus b here. On this side what is left? Y. Okay. And this 0 tells that in the second set of equations mu does not appear, which is fine. So, these two blocks together represent all these equations. Now, we say that this what is happening? One set of variables and the corresponding thing here in this vector is the cost component from here, linear coefficient of the objective function, and here the corresponding Lagrange multipliers. In the second row, the Lagrange multipliers come here and corresponding variables come here, that is these two have changed places. And here in place under the cost vector comes the vector from the constraint right hand side. Okay. This in this funny way these are paired x mu c b nu y. Now, all these funny things how do you remember? You do not remember, you just understand the logic. The sizes of the vectors which are coming in the corresponding positions should be same. You see x will have the same size as nu, because nu happens to be the Lagrange multipliers corresponding to these. So, as many x's that many nu's, and c also should have the same size, because you see at some point of time you did c transpose x, that means c was a vector of the same dimension as x. So, all those three fellows will appear in the similar places, and under them the variable set from the other family will come. Here it is the primal variables, here there will be the dual variables, here there are dual variables, so here there will be primal variables, and here there are cost factors, here there are constraint factors. So, this is the pairing. Anyway, so this is one funny thing that has been done. Another funny thing, do you notice? We actually forcibly took this a on the other side, and therefore, it became minus a. Without that, originally it was a. In the active set method, this fellow here was a. Now, in this particular instance, what we are doing is that for an originally symmetric matrix, we are doing something funny, something artificial to spoil the symmetry. Okay. But in any case, you will say that even when the symmetry were there, it was not of great significance, it was not of great use, because it was anyway not positive definite, it was an indefinite matrix because of these zeros. So, in the solution process that symmetry would not help anyway, but here we are actually killing that symmetry anyway. So, we have killed it. Now, what we have got? We have got this big system of equations, okay. And then we are calling this as z, this as q, this as w. So, this is m z plus q equal to w. Then we take this whole thing on the other side and say w minus m z equal to q, and that is appearing here. Okay. So, this set has been organized like this, with this z, this w, this q, this m, we have got this, and all the complementarity conditions together x transpose nu and mu transpose y are appearing as w transpose z. And since each of these w's and z's, that is nu's, y's, x's, mu's, since each of them is non-negative, so this essentially means that each of the elements w j, z j is 0. That means, both of them in one pair w 4 and z 4 together cannot be non-zero. So, at least one of them has to be 0. So, this is the complementarity. Okay. That is why this is a linear complementary problem. Now, the entire problem boils down to finding non-negative w's and z's which satisfy this complementarity conditions and this system of linear equations, that is all. And this point onwards, we do not talk about optimality, we do not talk about any less or more or all these things. We just try to find a solution for this system, solution which is non-negative w and z. Okay. Fine. So, find mutually complementary non-negative w and z. This is the one line problem statement. So, this is the requisition, we try to solve them. And as we try to solve them, to begin with, we make this observation: what if it happens that all these q's are non-negative? If all these q's are non-negative, then what happens? Then you say that if some of them are positive, some of them are 0, then you simply say z equal to 0, entire z equal to 0, and entire w then will become equal to q. which is fine, which is acceptable, positive or 0. So, if q is non-negative, then you have got a solution immediately in hand, w same as q, non-negative, and the corresponding z is 0. So, the entire z 0 will obviously satisfy this, and the corresponding w equal to q is will be satisfying this, and all of them are non-negative. This is entirely 0 and this is non-negative. So, you are done. Problem arises when this is not so, and that gives you Lemke's method, which is again a musical chair kind of method, very much like linear programming. So, what you do, in order to still do your favorite thing, putting all z equal to 0, you introduce an artificial variable z 0, and in all these equations, you put minus z 0, minus z 0, minus z 0, minus z 0. So, that is minus z 0 into this whole thing e. So, you put this, and now you say that what we will do, we will say we take z 0 equal to the absolute value of the worst positive fellow here. For example, if q, say q happens to be this vector 3, 0, minus 1, 4, minus 5, 7. So, we wanted the q's to be non-negative. This is so, this is so, this is not so. This is so, this is not so, this is so. So, these are the two offenders, and this one is the worst offender, minus 5. So, this q value, this entry of q is the worst. Now, what we can do, if we add 5 to all of them, then this will become 8, this will become 5, this will become 4, this will become 9, this will become 0, and this will become 12. If we add 5 to all of them, then all of them will become like this, and the worst will be 0, which will be fine. So, that is what is in a way achieved artificially by including this. Okay. Now, z 0 in this case is 5. Okay. So, make z 0 is equal to 5, and that means that in that equation minus 5 will come here, and that will cancel this minus 5. Basically, this fellow will go on this side, q plus e times z 0. That means, q plus a vector of z 0, z 0, z 0, z 0, and so on. So, to all of them z 0 gets added. In this case 5 gets added. Okay. So, then all of them will become 0 after addition of this on this side, and that is what you wanted, and then you say now z equal to 0 and w equal to whatever is on this side. So, now z 0 you have taken as this, and that gives you the rest of the vector z equal to 0 and w equal to this much, which is non-negative, and this you consider the basic feasible solution. However, this cannot be taken as your solution by which you go to the town and start manufacturing your system, because this has an artificial variable, which is causing the genuine variables to have artificially wrong values. Okay. So, you have to do something, and what do? You notice that in this pair w j z j, at least one of them had to be 0. Now, in this particular case, in one particular entry, both of them are 0, okay? Because in order to handle the worst q here, you have taken z 0 as just 5, not higher than 5. Higher than 5 also will handle this, but that is not what you do. You take exactly 5 to make it 0, okay? And therefore, after you put z equal to 0 and w equal to this, so one element of w also turns out to be 0, that element. Okay. So, now you find that if that w is 0, then that corresponding z could be made positive. It does not have to be set at 0. So, you have a freedom there, just like in the linear programming problem in the simplex method you had a freedom along one edge. So, here you have a freedom, you can increase that z, the w corresponding to which is sitting at 0, though it did not have to. So, typical musical chair here goes on like this. So, artificial z 0 drives out a w, say w 1. So, you put the logic that z 1 can be increased, because w 1 is anyway 0. Okay. So, z 1 can be made non-zero. So, you increase that, and while you increase it, you check, you go on checking how far we can increase it without violating any of the equations here. Okay. So, the first equation or the first variable value, corresponding variable value of the other variable hits 0, that is which is currently non-zero, by increasing z 1 as you go on decreasing some other guy from non-zero to something. So, up to 0 you can do that. Okay. So, the first fellow which hits 0, that says that below this you cannot go. So, that means above that z 1 cannot go. So, suppose w 2 hits the boundary first. So, as z 1 comes in, w 2 goes out. Then you will notice that well, now w 2 has come in, the w 2 has gone out, w 2 has become 0. So, z 2 can be increased. Then you increase z 2, and then perhaps w 3 becomes 0, that is the first that hits the boundary. Okay. So, then you say fine. So, z 3 can be increased, and as z 3 gets increased, perhaps z 0 is driven out. The moment this artificial variable is driven out, either at the end last iteration or even before that, the moment artificial variable is driven out, the solution that you have in hand, that is your solution, and that is a converged solution, that is the minimum point. Now, it may happen that in one step, the moment you start, you are stopped by some of the constraints, because some of the other variable is hitting the boundary. Okay. And by that time you had not driven out z 0, z 0 is still in the basis. In that case, that will mean that this problem does not have a solution. Okay. It does not have a feasible optimal solution, this is what it will mean. Okay. So, with this, let us see a very simple example, which will cover all the three cases. That is, and by the time this loads, I make another note here. These are the steps that I have already elaborated. Out of a pair of w and z variables, only one can be there in any basis. At every step, one variable is driven out of the basis and its partner called in. The step driving out z 0 flags termination. Okay. And now, one question we revisit, what about handling equality constraints? And this is indeed very clumsy. Any typical slack variable strategies handle equality constraints in a very clumsy manner. What it does is that if you have an equality constraint in your problem, then that is replaced by two inequality constraints. Okay. So, something should be equal to 0. So, you replace that single equality constraint as something should be less than equal to 0, and negative of something should be also less than equal to 0. That means, something should be less than equal to 0 and something should be greater than equal to 0. So, both the things you tell for that, and that artificial way is the way in which you take care of an equality constraint in this linear complementary problem strategy, this slack variable strategy. Anyway, so in this particular case, we will take this problem. The direct method first, that means constraint only equality constraint. So, consider this quadratic objective function and this single constraint. Well, single constraint only we will take, because the objective function itself is a function of two variables. Okay. So, you write the KKT conditions the way we wrote. So, you differentiate this and so on. So, these are the first two rows which are the gradient condition. Okay. So, that is 4 x 1 minus x 2 plus 3 lambda equal to 14 and so on, the second one. And the third equation is basically this. Okay. So, that is 3 x 1 plus 5 x 2 plus 0 lambda equal to 15. This is three equations, 3 unknowns, you solve them and you get this, and that is the solution. In one step you get the solution. So, that is the solution of the problem of minimizing this function for which the contours are shown here, subject to the condition that the point has to lie on this line. Okay. So, this is the point, you know, the point of tangency. Okay. And here the unconstrained minimum would lie at the center of this ellipse or at the center of each of these elliptic contours. Okay. Now, what we do? We replace this equality by less than equal inequality and then try to solve it by the active set method and slack variable method. So, minimize this subject to this inequality constraint. So, here q is this, c is this, minus 14 0. Okay. And suppose we take the initial point as origin. Okay. So, at 0 0, 0 plus 0 less than equal to 15 satisfied, and it is active inactive because 0 is less than 15, much less. Okay. So, there is no problem there. So, it is inactive. So, right now at this iteration, at the first iteration, no constraint is active. So, fine, no constraint is active. So, when you basically want this, you simply solve an unconstrained problem, okay, and find d 0. So, that is this. Okay. So, you find d 0 something, and from that you get x 1 equal to 4 2. That means, from here 4 2. Note that this is actually the center of the elliptic contours. Okay. So, but then this point is infeasible, because as you put 4 2 here, 12 plus 10 22. So, it is violated. So, this point is infeasible. So, you cut. The process to cut is you propose x 0 plus alpha 0 d 0, okay, and x 0 plus alpha 0 d 0 and solve this. Okay. So, 3 times 0 plus 4 alpha 0 plus and so on. Okay. So, just put this thing here in x 1 x 2 and solve this, and you get alpha 0 equal to 15 by 22, you will get it, okay, because you want 15 and you got 22 here. So, by 15 by 22 fraction if you take, then you will get this point, but this is not the optimal point. Okay. This is just cut from here. So, then you say that now this is our next iterate, and we propose x 2 as x 1 plus d 1, and there when you put this in the objective function and constraint function properly, then you get the task of minimizing this, okay, half d 1 transpose q d 1 plus g 1 transpose d 1 subject to this equal to 0. That means, now you will stay on this line, that is, you will keep this constraint active in this iteration, and then when you set up the KKT condition equations, you get this and then you solve. So, you get d 1 and the corresponding lambda, you get the d 1 and corresponding lambda like this. Okay. So, basically from here you go here, okay. And now you have got this point, and here nothing is violated, because you have kept the constraint active, and the Lagrange multiplier, that is important. Lagrange multiplier is positive 0.33. So, this is fine, this is a KKT point, this is the solution, and you have got it. Okay. Now, how do we do it by the other method, slack variable strategy? There we, to begin with, we put these constraints, which was incidentally not part of the original problem. Now, we put it and we do all these business and get this big matrix, the 3 equations, and on this side you see q minus 14, 0, 15. This is bad. So, we say z 0 is 14 and then this becomes 0, 14, 29. Okay. And then conduct a round of elementary row operations to get the identity and so on, exactly the way we do in linear programming problem. And first round z 0 came in, it drove out w 1. So, then we bring in z 1 through this step and you will find in this step w 2 goes out. Okay. And then since w 2 went out, we bring z 2 in and z 2 drives out w 3. So, we bring in z 3 and z 3 drives out z 0. The moment z 0 is driven out, we have got the solution and that solution is this. Okay. So, follow this solution steps carefully and you will get the entire picture step by step. In fact, not only follow, you should do it on your own by putting the appropriate logic at each point. Okay.